Hi everyone, today we'll talk about Chapter 21, Introducing Astronomy, Looking Beyond the Earth. This chapter will discuss the history and modern view of astronomy, the movement of objects in our solar system, and the measurement of different signals from space. Astronomy is the systematic study of the universe, or cosmos, meaning all of space and all of the celestial objects within it. So the figure below shows different pictures of stars, planets, and galaxies within the universe. Of course, the picture on the right is the Milky Way galaxy, our galaxy. In order to understand modern astronomy, we must understand the history of astronomy. So something called the geocentric model was the idea that the Earth was the center of the universe and other celestial objects orbited around it. This model was produced by Ptolemy who lived from 90 to 186 Common Era, and this dominated Western thinking in the Middle Ages. The heliocentric model is the idea that the Sun is the center of the universe. This was proposed by Copernicus and demonstrated by Copernicus between 1473 and 1543. Of course, we know that our Sun is not the exact center of the universe, but it is the center of our solar system. Although Copernicus's model was correct in that Earth orbits the Sun, it still had several issues. Kepler developed a model with three laws using ellipses that accounted for the deviations between a model using circles like Copernicus's and Ptolemy's and actual observations made from looking at the sky over long periods of time. Kepler's first law is that the orbits of planets are ellipses with the Sun and one of the ellipses two foci. The second law is that the orbit of the planet sweeps out equal areas over equal time. And the third law states that the square of the orbital period of a planet P is directly proportional to the cube of the semi-major axis of its orbit A. Here's a pictorial example of Kepler's first law. We have Earth orbiting the Sun in an elliptical track, which is represented by the blue ellipsis, and then the Sun being one of the two foci within the ellipse. We have BE and AE points representing the semi-major and semi-minor axes, and BD and AC points representing the major and minor axes, respectively. The center of the ellipse is at point C. It's important to note that the ellipticity of this picture is exaggerated compared to real life. The Earth's real orbit is almost circular with just a very, very slight deviation towards an ellipse. If Earth's orbit did actually look like this, the different seasons of the year would produce drastic temperature differences on Earth that would make Earth uninhabitable for life. Notice that this exaggerated ellipse is used throughout multiple examples throughout your textbook. Kepler's second law is the orbit of a planet sweeps out equal areas over equal time. This means that an imaginary line connecting the Sun and the planet will sweep over equal areas even though the length of time the line changes. This implies that planets move faster when they are closer to the Sun. So during time A, we're part of the aphelion, which is known as the slowest motion of the planet because Earth is furthest away from the Sun. Whereas point B, we're slightly faster, and through time period C, known as the perihelion, the Earth is in its fastest motion while it orbits the Sun throughout the year. The perihelion distance is shown as well. Kepler's third law of planetary motion states that the square of the orbital period of a planet P is directly proportional to the cube of the semi-major axis of its orbit. So here we have shown the orbits of Earth and Mars around the Sun, not to scale. Then we have the center of Earth's orbit and the center of Mars' orbit, slightly off from the center of the Sun. So Mars' semi-major axis is 228 million kilometers, with the duration of its orbit being 687 days, whereas the Earth's semi-major axis is 150 million kilometers, with the duration of its orbit being 365 days. So in short, the square of the length of time, or the length of time of orbiting, is directly proportional to the length of the semi-major axis. After Kepler came Isaac Newton, who made many contributions in the fields of physics and astronomy. So one of the inventors of calculus, discovered this color spectrum within white light, invented the reflecting telescope, which we'll discuss later in the lecture, and proposed 3 laws of motion in the universal law of gravity. Newton's 3 laws are described as follows. His first law is that every object has an inertia, meaning that an object at rest will stay at rest, or an object in a straight line motion will remain in a straight line motion unless changed by the application of a force. The second law is that when a force acts on a mass, it causes the mass to change speed and/or direction, meaning that it causes an acceleration. This law can be written as F equals ma. Newton's third law states that for every action there is an equal and opposite reaction. Newton's law of gravity states that every object in the universe attracts every other object. Gravity is proportional to the gravitational constant g, the masses of the 2 objects, m1 and m2, and inversely proportional to the distance between the centers of the mass of the objects, r squared, producing the formula below. In the 18th and 19th centuries, new and better telescopes were constructed, producing a better picture of our solar system and its structure. The Milky Way was identified as the galaxy of stars of which our Sun is a part. Galaxies consisting of hundreds of billions of stars were discovered as astronomers learned to measure distances to celestial objects, for example, the M81 galaxy on the right. The Big Bang Theory, which is a scientific model for the origin of the universe, originated in the mid-20th century. These points represent a general view of our modern understanding of astronomy. To help visualize astronomical concepts, we use something called the celestial sphere. The celestial sphere is an imaginary surface in space that surrounds the Earth and is used to portray objects in space relative to the Earth. Importantly, it is oriented to the Earth's axis of rotation. So the figure below explains the following. The celestial poles, both north and south, are directly above Earth's geographic poles, above and below. Stars appear to lie on the celestial sphere, but they really are lying at different distances from the Earth, from one another, shown by the different yellow lines coming into and out of the sphere. The celestial equator is a projection of Earth's equator into space. And finally, the blue line at an angle of 23.5 degrees relative to Earth's equator is known as the ecliptic plane. The ecliptic plane is the Sun's apparent annual path around the celestial sphere. This is apparent because it aligns with the plane of Earth's orbit around the Sun. So the celestial sphere is used for us to be able to help understand or put in perspective or project, or to be able to project where the stars are and different other celestial materials are relative to Earth. The apparent movement of the Sun across the sky occurs because Earth rotates on its axis. One solar day is equal to 24 hours, and the solar day is defined as a return to the same alignment with the sun. One sidereal day is 23 hours and 56 minutes, and this is defined as how long it takes the Earth to rotate on its axis. The difference between these results in us having to add an extra day to the calendar every 4 years, known as a leap year, so that the sidereal days and solar days keep alignment with one another. Now let's describe Earth's orbit. The eccentricity of Earth's orbit is so small, 0.017, that it is actually almost circular. Eccentricity is defined as how stretched out an ellipse is compared to a circle. So here's a picture of a perfect circle surrounding the sun and Earth's orbit, which is slightly eccentric, 0.017. Here's another view of the ecliptic plane. Earth's ecliptic plane is the trace of the apparent path of the sun as it moves across the celestial sphere during the course of the year relative to the celestial equator. It is tilted at 23.5 degrees relative to the celestial equator. The sun's path varies with latitude and season. To help you visualize this, see the pictures on the right. Since the tilt of the Earth's axis of rotation does not change as the Earth orbits the sun, the arc that the sun takes across the sky, from the perspective of the observer, varies with both latitude and time of year. Duration of daylight also varies with latitude and time of year, as was discussed in our chapter on climate and seasonality. So if we look at the picture, in the top picture we're viewing from the Arctic Circle 66.5 degrees north. We see that the sun does not extend very high into the sky in both the equinox and summer solstice and winter solstice. However, if the sun is viewed from 35 degrees north, closer to the equator, we see the sun in each of these portions, or each of these times of year, is somewhat higher and takes a somewhat longer route across the perspective's vision. If viewed from the equator, at the equinox, the sun is directly above the observer's head, where the winter solstice and summer solstice are still relatively high, but not directly above. The solstices and equinoxes were discussed in the chapter on climate change that included seasons, but they're worth mentioning again. An equinox occurs as the Earth's axis transitions from being tilted towards the sun to away from the sun, or vice versa. The equinoxes occur around September 22nd and March 20th, and since equinox means equal night from Latin, these are meant to describe the days of the year in which day and night are approximately equal times all over Earth. A solstice occurs when Earth is at its maximum tilt toward or away from the sun. These occur around December 21st and June 21st, indicating the longest days or shortest days for a particular hemisphere. Precession is the rotational axis of the Earth wobbling like a top. It takes 26,000 years for the Earth's axis to make a complete circle in the wobble. As a consequence, the North Star changes over time. You can see Vega was the pole star or the North Star in 14,000 Common Era, whereas today Polaris is the current pole star or North Star. Constellations are a grouping of stars organized into recognizable patterns. Here's one example of the constellation Orion. The zodiac are 12 constellations that lie along the ecliptic plane described in previous slides. The sun and the planets appear to move along this path through the sky. So as an example, on September 1st, the sun is seen in the direction of Leo constellation as viewed from the Earth. The apparent path that the sun follows against the background of the stars is called the ecliptic plane. By December 1st, the Earth has traveled far enough in its orbit so that the sun is seen in the direction of Scorpius, indicating that that is the month for Scorpius. This is a very interesting slide, showing the movement of the planets in an angle against the horizon. The planets appear to wander through the sky along the ecliptic, so if you see the sunset in one direction and you see several stars, or what look like stars, lining up in parallel as some of the first stars that you see, these may be the planets lining up on the ecliptic plane. So you're taking a look at a good bit of our solar system by looking at this photo. The concept of retrograde motion is the occasional movement of planets in a reverse direction, east to west, on the celestial sphere. Now, this doesn't mean that the planets actually change their direction of motion as they orbit the sun, but what happens is because there are the planets orbit around the sun at different velocities. So at times, the Earth may be moving ahead in its orbit slightly compared to other planets like Mars. This produces, in our view in the sky, the retrograde motion as seen in the figure on the bottom. Notice the points A, B, C, D, E, F, and G. Sometimes Earth is in front of Mars, sometimes Earth is in line, and sometimes it is behind. Now let's discuss the moon's rotation. The visible moon is a familiar feature, and it orbits around the Earth in 27.3 days. It is tidally locked to the Earth, so we only ever see the same side of the moon. It turns on its axis and orbits the Earth in the same length of time on the right. So we see the side that has the Mar and the Highlands, as shown on the light side of the moon. We don't see the dark side of the moon because we're rotating in the same direction at the same pace, more or less. It's important to know that the tides that are brought on by the moon are the movement of Earth relative to the water as Earth is spinning. The moon's orbit is shown in the figure below, and it moves in an east-west along a path oriented about 5.2 degrees angle to the Earth's orbital plane. So here we have the ecliptic plane, the celestial equator, and the moon's orbital plane, all in slightly different planes. Now let's discuss the phases of the moon. The moon is visible because of reflected sunlight. So if we look in the picture, you have to squint to see the moon. On the right, you see the sun's rays, and then the Earth, and then the moon. As the moon orbits the Earth, different amounts of it are visible as the angle between the sun, Earth, moon changes, which produces a visible cycle called phases. And this cycle takes 29.5 days. At a full moon, the whole moon is visible, and at a new moon, none is visible. So at the top and the bottom of the figure, we have examples of new moons. The reason is that we are seeing only, we can't see any of the moon because it's in the shadow of the sun. It's sort of directly in between the Earth and sun. However, at a full moon, we see the Earth is directly between the sun and the moon. In this case, we are seeing at nighttime the reflection of the sun off of the one side of the moon. As we go back into a new moon phase, we're seeing partial reflectance of the sun off the moon, giving us our different quarters and waxing and waning, gibbous and crescent. Now let's discuss eclipses. An eclipse occurs when the moon or the Earth passes through the other's shadow. Normally, the moon's orbit is tilted compared to the Earth, so it does not cross the Earth-Sun line. However, an eclipse can occur when the moon crosses the Earth or the sun during a new moon, which is known as a solar eclipse, or a full moon, which is known as a lunar eclipse. So the figure on the top and the two figures on the bottom are related here, where you see during the new moons we have at some times a year we have unfavorable moments for an eclipse where you have new and full moons having their shadows not interacting with the Earth, and the Earth's shadow not interacting with them. However, at other times, when we are crossing that those two orbital planes are intersecting with one another, we have the potential for the shadow of the moon to block out portions of the sun from the Earth, or the shadow of the Earth to block out light from the sun against the moon. A solar eclipse occurs when the moon passes directly between the Earth and the sun at a new moon. The distance between the Earth and the moon determines the type of eclipse seen. In the figure below, T is the area of the total eclipse and P is the area of the partial eclipse. Annular eclipses occur when the moon is too far from the Earth to completely block the sun. In the diagrams also, umbra and penumbra refer to the angular distances caused by shadows. Here we have a lunar eclipse where the sun is passing behind the Earth, blocking the light of the sun during a full moon. Here the moon looks red because sunlight that passes through the Earth's atmosphere is bent towards the moon and is reflected off the surface of the moon. For part 2 of the lecture, we'll discuss the electromagnetic spectrum. The electromagnetic spectrum is the entire range of wavelengths of electromagnetic radiation. Electromagnetic radiation travels in the form of waves that can travel through a vacuum, and different types of electromagnetic waves are distinguished by their wavelengths. Visible light is a small portion of the spectrum and the part of the spectrum that can be detected by our eyes. Atmospheric gases absorb or reflect most wavelengths of electromagnetic radiation. There are only two regions of the spectrum that are easily observed at Earth's surface. The radio and visible waves are not blocked and referred to as the radio window and the optical window. White light is a mix of different wavelengths or colors of light. When passed through a prism, they can be separated, shown in the figure on the top. This is useful for astronomers because different objects emit or reflect different wavelengths of light in different ways, which is shown on the bottom. We have a continuous spectrum, an emission spectrum, and an absorption spectrum. The Doppler effect is a shift in frequency caused by the movement of either a source or an observer. So the Doppler effect is best explained through a metaphor of a train whistle, where if we have a stationary whistle, the sound radiates out in all directions equally. However, if the whistle is moving, then the radiation of sound may seem to cover shorter distances in the direction that the train is moving. Now transitioning this to astronomy, if a light source moves toward an observer, the radiation detected by the observer will be shifted towards shorter wavelengths. This is known as blue shifted. If the light source moves away, the radiation will be shifted towards longer wavelengths, which is known as red shifted. Waves that reach the observer and that are blue shifted are squeezed, whereas red shifted waves are spread out. Doppler shifts are very important concepts in astronomy. The shift in wavelengths between radiation from a distant source, such as a galaxy or star, and from the sun, can be used to determine the velocity of the source's movement toward or away from Earth. So here is the wavelength spectrum from the sun compared with that from a distant galaxy. Now let's discuss the units that astronomers use. One astronomical unit AU, is defined as the average distance from the Earth to the Sun, which is 150 million kilometers or 93 million miles. 1 light year is the distance that light travels in a year, which is 9.5 trillion kilometers or 5.9 trillion miles, or 63,225 AUs. A parsec is 3.26 light years. Because the distances in space are so vast, the further away you look, the farther back in time you are looking because of the time the light from an object has taken to reach us. The light from our own sun, for example, takes about 8 minutes to reach the Earth's surface. Now, how do we measure distances in space? There are a variety of methods used to measure distances, and these techniques are used at varying distances from near to far in the order they are given below. Radar are signals bounced off of nearby objects, and the time it takes for the signal to travel there and back can give us distance to the object. Radar is radio detection and ranging, so these are within radio waves. We'll discuss the geometric parallax more on the next slide. The stellar brightness is another way to measure distance. Stars have an inherent brightness. By comparing this to the observed brightness, we can estimate distance to the object. Cepheid variables are variable stars with an intrinsic brightness related to their own variability. They are very bright, so can be seen from great distances. This is a variation on stellar brightness that can be used to measure distances in other galaxies, to other galaxies. Then finally, we can use Doppler shifts to estimate distances to very far away galaxies because the amount of redshift is related to distance. Geometric parallax describes the idea that a nearby star shifts its position relative to the background stars when viewed from opposite side of the Earth's orbit. By measuring the angle it is shifted by with the distance a to b, we can use basic trigonometry to find the distance to the star. This is also the origin of the parsec. 1 parsec is the distance of an angle of 1 arcsecond of shift in the diagram. So here we have the analogy of the right eye view versus the left eye view if we close one of our eyes. We notice that the view changes. Then we look at it in the context of different points on Earth's orbit. We can see that the views are different and calculate this. We'll end our discussion on the introduction to astronomy with several slides about the telescope. Telescopes are instruments for collecting the light of distant objects to make them visible to us here on the Earth. There are several types of telescopes. Optical telescopes collect visible light. These use lenses, which are refracting, or mirrors, which are reflecting, to collect the light. Radio telescopes collect radio waves, and space telescopes observe space from above the atmosphere, and without atmosphere to block or distort incoming light, they can detect all wavelengths. Here's a picture of a refracting telescope. Refracting telescopes were first developed in 1608 by Galileo to observe Jupiter's moons. Incoming light is refracted or bent through curved lenses and concentrated on a focus behind the lens. The second lens, the eyepiece, creates an image for the observer. The reflecting telescope was developed by Isaac Newton. Reflecting telescopes use a curved mirror to reflect light to a focus in front of the mirror, as shown below. Air in the atmosphere is always in motion and changes in temperature and humidity. As a result, the path of light passing between space and an observer on the ground is altered, causing images to be slightly distorted. Additionally, the bright glow of artificial lighting can wash out the faint light coming from distant objects. Many more objects will be visible further away from artificial lights. This density of artificial lighting created by humans is known as light pollution. We have several large observatories on Earth that employ optical telescopes, like the Paranal Observatory in Chile, Mauna Kea in Hawaii, and Roque de los Muchachos in the Canary Islands in Spain. Radio telescopes are used to collect longer wavelength radio waves. Modern radio telescopes consist of a dish that reflects incident radio wave energy to a focus where instruments collect and analyze the signal. Because radio wave energy is weak and the wavelengths are long, radio telescopes need to be very large. Example is the National Astronomy Laboratory in West Virginia, which has a dish that is 105 meters in diameter. Because radio waves are very long, astronomers often combine the signals of many separate radio dishes to produce a better image. This is known as interferometry. One example is the Very Large Array, a radio interferometer in New Mexico. Finally, we discuss space telescopes. Space telescopes are placed on satellite or spacecraft that orbits above Earth's energy-absorbing atmosphere. These telescopes have the advantage of being able to detect the entire electromagnetic spectrum, including gamma rays, X-rays, and some longer wavelengths like infrared that can't pass through the atmosphere. One example is the Hubble Space Telescope. Another example is the recently launched James Webb Telescope.